When is the worksheet due? Like the one with the periodic table?
It's due on the same day as exam. Hold on a second. Let me check that.
Okay, that was the only thing I couldn't find a due date on.
Yeah, it is missing. Let me see. Periodic table. Okay. I introduced that one a little early. The material for that extra credit for the periodic table won't come until chapter 4. And also for the naming the compound won't come until chapter 4 and 5. I think that's old. So it's not due. In fact, those 2 extra credits aren't due until the 2nd exam. Okay, so you got plenty of time.
Oh, okay. Thank you.
Yeah. Let's see. I got you in here now in print. Let me see who else we got. Washington and got Michaela twice. Okay. I'll bring it to you. Let's see. That's awful crooked. Do that. Let's see. We're recording. Did everyone get my email about the Brightspace and installing Respondus lockdown? Okay. I modified the syllabus so that if you go back into Brightspace and look at the syllabus there, it'll have the change. Prior to that, when we had Blackboard as our learning management system, we had to install Lockdown Browser before you could even open the exam. But now, the way Brightspace is set up, you can go into Brightspace, and the first time you click on an exam, preferably the practice test, there will be a place down there just above where it says take the quiz or start the quiz. And it'll say install Lockdown Browser, Respondus Monitor Lockdown Browser. And that's where you go in, just click on it and install it from there. That's the simplest way. In fact, it's a better way than we had before. Somebody, I don't know if it was in this class, it was in some class, discovered that the link I had in the syllabus was tailored to Blackboard, so it would install. And I've contacted IT and let them know, and they're okay with my method. Okay. Let's see, let me check to be sure I got everybody. Looks like it. I've got 4 students are signed up for the Cengage homework. Okay, I understand if you have to wait a few days, maybe you've got financial aid coming through and you can't buy the Cengage Unlimited until you get your financial aid. But don't get too far behind, because we're introducing chapter 3 today. Thursday we'll review, and a week from today we'll have the exam on those first 3 chapters. Right? So if you wait till then, you're getting pretty far behind. Okay. Any other questions or problems before I get started? Let's see. Turn that into a slideshow. Clear. And just as a reminder, when we review all this stuff on Thursday, we're going to be using this document right here, Exam 1 Review. You can find it in Brightspace. I know it's there. I was looking at it this morning. And I'll pick from that document, unless you have problems. If you work through those problems and you find yourself stumped someplace and you need extra help, then bring those to class and everybody else can benefit from the discussion. Otherwise, I'll go through and I'll pick out the non-redundant questions and use that as a guide to work over material that we've covered. Okay, if there are no comments or questions, we'll work on the very last chapter in this exam. We've already covered the introduction, measurements, and calculations, which is really common to all sciences. Now we're going to get into matter. I mean, what is the world made of? What is the universe made of? How do we classify it? How do we try to make sense of it? And this is material that is central to chemistry, but it's also valuable for other sciences as well. So we're narrowing down our focus, but we haven't quite got to chemistry yet as a standalone topic. All right. And we really only have a few topics, but they're kind of expansive. So it'll take us a little while to get through it. All right. Grade school. I remember the definition for matter from grade school. You know, anything that has mass and occupies space. Right? And this means it has a volume, right? Occupies space. This means that there's substance there. Something is there, as opposed to a vacuum where there's nothing there. And we use this term mass because that is the scientific term for stuff. If you have a measurement of mass, you know that there's something there. Whereas if we say weight, we're sort of inferring that there's something there, but the weight is variable. You know, it just depends on what gravitational well you find yourself in as to what the weight is. On Earth, I may weigh, unfortunately, 205 pounds. On the moon, I probably weigh something on the order of maybe 32 or 3 pounds. But I still have the same mass. Okay. Under normal circumstances, we know that matter exists in 3 different phases, right? Solid, liquid, and gas. There are other phases in the universe, but they're under extreme conditions, and we're not going to mess with them. Okay. And this is an artist's rendition of what you might expect to see. If you could get small enough and look at the individual atoms of a substance, if it were a solid, there would be there'd be an order, usually, not always, but usually there's some type of order to the atoms and molecules in a substance. Now, like I said, there are some things that are what we call amorphous. A is that prefix. A means not. It's a Greek prefix. So whenever you see a in front of a root word, it means just the opposite of the root word. So when I say amorphous, means it has no form, which just, it's a way of indicating that rather than a regular arrangement of atoms in the solid, it's still solid, but they're irregularly arranged. They're just random. We'll cover that a little bit later. What you need to know is what characterizes a solid, liquid, and gas. What sets them apart? Well, at the molecular level, it's the amount of energy each molecule and atom has, and the space that's between them. Right? So the space between these atoms is very close. This is a bad example because ice is a special case. Water is special, right? I'm not going to go into that right now. We will, though. But generally speaking, the atoms and molecules of a solid are very close together, and they're sort of locked in place. And if they have any energy at all, it's just vibration. They're just jiggling. Okay? Whereas liquids, the molecules and atoms are relatively close together, maybe a little bit further apart than a solid, but they have enough energy where they can slide past one another. They're not locked in place. That's why they, if you pour a liquid out on, if you dump a liquid on the tabletop, it's just going like that. Whereas if you do it with a solid, they'll just sit there. And gases are really the extreme. The molecules in a gas are very far apart, and they got lots of energy. They're moving very fast. Okay, so we characterize a solid as rigid. In other words, it holds its own shape. It doesn't need a container. Like an ice cube, or a diamond, or a chunk of metal, an iron bar. They're all solids. They can stand on their own. And they have a definite volume. In other words, as long as the temperature doesn't change, their volume is constant. The liquid still has a definite volume, but it does not have a definite shape. It cannot hold its own shape. So like I said, if you pour it out on a table, it's just going to go everywhere. But it won't change its volume unless it changes its temperature. So that's a given. You've got to maintain the same temperature in order to have the same volume. But it has no shape. It needs a container. Okay. Gasoline's a good example. Water's a good example. Blood is a liquid. Okay. So here we have the same liquid occupying different shapes. It's probably water. Gases, however, cannot hold their own shape and cannot hold their own volume. So in order to, if I say I have a gas here in my hand, you might ask me, what's its volume? I don't know, because it assumes the volume of the container, right? So you need a completely enclosed container to confine a gas and also give it shape. So if we inject a small amount of gas into a container that's evacuated and there's nothing inside, it's a pure vacuum, then the gas will expand to fill that space. If there's another gas in there, we'll talk about that in a minute, then you put a different gas in there, it will expand to fill that space. And the other gas will still be there. Okay, so those are our three phases. And we can say air is a gas. We know it's a combination of different elements. Helium's a gas, right? Everybody knows helium because as a kid, maybe as an adult, You go to a party and breathe out of a balloon and talk funny. Right? That's helium. And then oxygen. We have to have oxygen. Heterotrophs, that's the biological term for it, which means other eaters. Heterotrophs have to have oxygen because that goes into the process of breaking down the food and extracting energy from it. So without oxygen, we're in sad shape. Green plants, on the other hand, produce oxygen as a waste product. Their food is carbon dioxide. Right? So if the EPA wants to classify carbon dioxide as a pollutant, then they're off their rockers. Carbon dioxide is essential, but it is a gas at normal atmospheric pressure and room temperature. Okay, so we're going to draw a distinction between two terms here. One is property, and the other is, let's see, my mind's gone blank. That was when you get old. Let's see. Change. Property and change. Okay. Property of a substance refers to potential. And change is, well, by definition, it becomes something different. Okay, so let's talk about properties first. We can also subdivide properties into physical properties and chemical properties. In a physical property, the identity of the matter does not enter into the calculation. In other words, a physical property gives you characteristics of that matter that can change, right? They can change. But when they do, the identity of the substance does not change. So, for instance, if you have liquid water and it gets really cold outside, it'll go from liquid to solid, but it's still water. The identity has not changed. Or if it gets really hot outside, then it might turn to steam or evaporate. Right? Dump the rest of your soft drink out on a hot pavement in the summer. Pretty soon the water's gone, and you just sort of have a sticky blob left where the drink was. That's a physical property that describes the potential for change without a change in identity. And these characteristics are usually observable. In other words, our five senses can pick them up. You might see a change in color. You might see a change in phase that I just described. You might, here's a fun thing to do. Heat up a frying pan. Cast iron skillet's best on the top of your stove. You can get it hot. You can tell when it's hot. You can get close to it. You can tell. Really hot. Then you take a little water just from the faucet from your fingers and sprinkle it. Drop it on there. And it will instantly vaporize. There's so much heat there. You can hear it. You can hear it sizzle. Picking that up with your senses. But it's still water. Other examples, let's see if I missed any. Odor, all right, we can pick up smells. Characterizes, it's a physical characteristic. In other words, travel to green sulfur springs or white sulfur springs. You get close enough to a water source down there, and you'll probably smell hydrogen sulfide. And it is horrid to smell. In fact, I don't know, I guess you can get used to drinking anything, but I wouldn't want to have to drink water laced with that stuff. Color I mentioned. You can see a characteristic of a substance is its volume, right? The volume can change, especially for a gas. The volume can change if you change the shape of the vessel, but it's still the same gas. Its identity has not changed. Volume is a physical characteristic. Its state, its density. We haven't defined density yet, but density is mass per unit volume. In other words, if I have this amount of mass of something and it weighs a certain amount, it has a mass of a certain amount. And then if I have more of that substance, then it will have more mass. But the ratio of the mass to the volume will always be the same. That's density. Melting points and boiling points, those are physical properties. Now, we're not saying that you actually melt something or boil something, but you know at what temperature it occurs. And it has a potential to change. Okay, chemical properties. This describes the potential for a substance to become a different substance. And I mean, it changes identity. But we're not saying it changes yet. This is the potential. Chemical property is the potential for change. All right, what do we mean by that? Well, in order for a substance to change its identity, in chemical terms, let's see, how do I describe this without introducing a topic we haven't covered yet? Well, let's see what the wording says. That's true. Usually, when a substance changes, in chemical terms, it comes into contact with some other substance, and a reaction occurs. It doesn't have to. In other words, you can cause a chemical change, and you can define a chemical property based solely on that substance. But in order for us to describe that, let's say, if we say this sheet of paper is flammable, right? We know what that means. It'll burn. It's not burning now, right? But it has the potential to burn under the right circumstances, right? In an oxidizing atmosphere, oxygen's around. If we increase the temperature to 451 degrees Fahrenheit, it'll catch fire. Now, why do I know 451? Because there's a famous science fiction book called Fahrenheit 451. Y'all read it, it's good. There's a movie made about it too. So it describes the potential for a change of substance, of identity. Okay, other examples, I said flammability, rust. If we say steel has the potential to rust, okay, yeah, it does. Usually if there's water around and if there's a little salt, it's even better. And there's oxygen around, steel will change its identity from iron, primarily, to iron oxide. Okay. Did I tell you about that building in Atlanta yet? They called it the Omni. Some architect had the bright idea to build a building in Atlanta. That's where I grew up. Part of my life over there. And a new technology had developed that was sort of based upon stainless steel. In other words, if you make the substance a certain way, then it will do this change. In case of steel, it will rust so fast that it will seal off the surface of the metal. No more air can get to it. And from then on, you won't have to paint it because it won't rust any further. The problem is, whoever this bright architect was didn't realize what happens when iron combines with oxygen. If it retains the same volume, then it will stick and stay. But rust has the tendency to expand when it forms, which means it flakes off the surface. So this rust formed on the surface of the steel, and it looked great at first. I mean, it's nice, kind of a brick red color against the background of all these other gray and glass covered buildings. Except Atlanta gets a lot of rain. It's like between 30 and 50 inches a year. And pretty soon there were red streaks all across the concrete because that rain was washing the rust off of the building and it was staining the concrete. So they hung on for a little while and finally tore the building down and put something else up. Food is digestible. That's a chemical property. It can be changed. If we ingest it, then there are certain processes that go on inside which break the food down and extract energy from it. So those are chemical properties. Okay, let's see if we can classify these as chemical or physical property. Ethyl alcohol has a boiling point of 78 degrees centigrade. That's a physical property, right? If we boil it, it's still ethanol. It's still ethyl alcohol. That hasn't changed. Hardness of a diamond. That's a physical property, right? You're not changing diamond. In fact, you're using it to scratch a surface. In fact, diamond is the hardest naturally occurring substance. And other substances are much softer. And on the low scale, let's see, I think that's how you spell it. The Mohs scale, diamond is a number 10, and talc is a number 1. That's the softest substance on that scale. Now, talc is what they used to put in powder. Dust it all over your body until they found out that some people are susceptible to the formation of cancer. So they had to stop doing that. Now they use starch. But they also use talc to make ceramic tiles, backsplashes in your kitchen, floor, tile floors. They use talc to make that. Plus they add some other ingredients. So it may not stay hard. Right? I mean, it may not stay soft. Once you form it into a ceramic, now you've actually changed the subject, and while we're on the topic, it's no longer talc. You've changed its identity to some ceramic that's very hard. So that would be a chemical change if you actually go through that firing process. Okay, hardness of diamond, that's physical. Sugar ferments to form methyl alcohol. Every moonshiner knows this one. And that's a chemical property. It's fermentable sugar. Now, if that moonshiner wants to extract the ethanol from the mash, right? What do? They heat it up, and the ethanol undergoes a physical change, actually, based upon this physical property. Then the ethanol undergoes that physical change from liquid to gas, and then comes over, condenses into the thumper and out the bottom and the mason jar, and they swirl it around, cap it, shake it up, and they can tell by looking at it roughly what the proof is. Also, what they want to do is when that first fraction comes off of the boil, throw it away, because that's not ethanol. That's methanol. It has a lower boiling point, comes off first, and that's the one that is called wood alcohol. If you drink that, you go blind. If you drink enough of it, it'll kill you. This is the drinking kind right here. Okay, so now we go to physical change. For this, we're talking about actual let's see what's the right word. The realization of this property is the change. So it changes the physical form somehow, but it still has the identity of the substance. So if you boil water or freeze water, that's a physical change. Based upon what? Based upon the physical property of the boiling point or the freezing point. Here we have our three states of water again. The water molecules are still there. It's still water, no matter what phase it's in. What changes is the energy of the individual molecules and the distance between them. Now, a chemical change requires that you have a new substance. The identity has changed. It has different properties. It may have different physical properties. It definitely has different chemical properties than the source. Methane. Everybody knows methane, natural gas. Right? If your house is piped into a gas pipeline, it's going to be predominantly methane that's coming into your house, goes into your water heater, into your stove, into your gas dryer, and it burns and releases heat. And when it does that, it undergoes a chemical change. We're going to learn how to do this. There's your methane, there's your oxygen, and it makes carbon dioxide and water. Chemical change. It's not methane anymore. It's not oxygen anymore. I mean, it's not elemental oxygen. Now oxygen is combined with hydrogen and carbon. So this represents a chemical change, and we're going to learn how to do that. So don't fret yet. We're building up to it. Besides, that's not balanced anyway. Okay. We can cause a chemical change. I used to have one of these contraptions. Well, it wasn't mine. It belonged to the school. I taught high school for 1 year. That was enough. And we had a device that used this as a demonstration. And you have distilled water in this device, and you connect a battery to it here. So one electrode is, let's see, this one's negative and this one is positive. And you put a little acid in there. Hydrochloric acid's fine, vinegar will work, just so that the current will pass through the water, because pure water is an insulator. Right? If you, for instance, if you have distilled water in a beaker and you drop a 9-volt battery into it, nothing happens. If you add a little lemon juice or a little hydrochloric acid, and now it conducts electricity, pretty soon you'll see bubbles forming at the poles of that 9-volt battery. It's doing the same thing this device does, right? At the negative pole, you get hydrogen gas, and at the positive pole, you get oxygen gas. And you can test to see, once it forms up here, you can open the stopcock and use I don't know if you've ever seen a burning splint. It's like a wood stick, and it's specially treated so that you light it on fire and you blow it out, and it still glows. Right? So there's enough energy there to elicit a response. So if you put it in the gas coming out of this one, it'll burst in flames because oxygen supports combustion. If you put it in this one as a glowing splint, it'll pop because it ignites the hydrogen that is now combined with the air, and actually it goes back to water. Right? That's why they say the hydrogen economy is the most environmentally benign, because you can form hydrogen by electrolyzing water if you have an energy source. And then when you burn hydrogen or run it through a fuel cell, you get water back. So it's like a continuous cycle. What you need is an abundant source of cheap energy. And right now, the best source is nuclear power because it produces no gaseous byproducts at all, only waste heat. Okay. So we're decomposing water into these two substances. They change their identities. That's a chemical change. And this is what it would look like if we could get down small enough to see it. It may not look exactly like that, but this is an artist's rendition. So you take two water molecules and you make one oxygen, diatomic oxygen, and two diatomic hydrogens. Remember when I showed you the periodic table? And I mentioned those blue backgrounds, these elements? Those are the diatomic elements. At room temperature and atmospheric pressure, there are always two of them bound together. So the hydrogen and oxygen on that table, when you write them out, if you read a word problem, it says hydrogen and oxygen are combined, ignited to make water. If you don't write them like this, O2 and H2, then you'll never get that equation to balance. Okay, that's just a heads up, it's coming. So how many of these are chemical change? Pulverizing rock salt, which is what they have to do before they spread it on the roads. You know, make it, actually they're pretty big chunks. You can see them as they come out of the back of the truck. That's a physical change, right? Burning wood. If wood burns, it's undergoing a chemical change. Primarily cellulose is combining with oxygen to make carbon dioxide and water. Unfortunately, there are other things in wood. There are minerals in wood, forms an ash. If you don't have enough oxygen, then you get incomplete combustion and you're going to produce soot, which is basically carbon, graphite. And that's what coats the inside of your chimney because the combustion is usually incomplete. Unless you have one of these modern stoves that has a built-in catalyst. And then anything that goes through that catalyst is continued to break down into carbon dioxide water, and you don't get a soot buildup in your chimney. But if you have an old-fashioned fireplace, then periodically you need to have somebody come in and scrape it out, clean out that soot so you don't have a chimney fire. So that's a chemical change. Dissolving of sugar in water. It's a physical change. Right? When you put sugar in water, it's still sugar. How do you know? All you have to do is just let it sit out on the countertop and let the water evaporate, and eventually you get all your sugar back. Melting a popsicle on a warm summer day, that's a physical change. It's still got the same ingredients, it's just they're all over the ground or all over your hand, on your kid's face, whatever the case may be. Okay. Sugar fermenting to form ethyl alcohol. That's a chemical change. Right? We're changing the identity of sugar to ethanol plus some other stuff. Iron metal melting. It's a physical change. It simply changes its state. Now it does so at very high temperature, but it's a physical change. When iron combines with oxygen to form rust, we know that's a chemical change. Check my list occasionally to be sure. Is anybody okay? Good. Chemical, physical, chemical. Okay. Now let's start. Let's dip our toes in the chemistry pool. Matter that we've defined in general terms is made up of elements. What is an element? Well, we know how to induce physical change and chemical change. So with chemical change, we're going to change the identity. But if we use both physical and chemical means to simplify a substance, break it down. We use physical means first, like we subdivide it physically, like knife cut, like that. If the substance is elemental to begin with, then you can use physical means and break it down until you have one representative of that element left over. That's the atom. If you have a combination of substances like water, hydrogen and oxygen together, you can subdivide it down to smaller pieces of water, but you can't get to the element without chemical means, like electrolysis that I showed you before. You got to break that hydrogen and oxygen apart, break a bond. But once you do, you get down to the elements of which that compound is composed, hydrogen and oxygen. Those are elements. They cannot be broken down any further by chemical means. If you break an atom any further, an element, if you reduce an element further, you need nuclear means. Right? And we'll introduce the topic, but it's not the main focus of our discussion in this class. Okay, examples of elements. All right, iron. Notice they've got symbols goes with them. Right? So those elements are represented in the periodic table. In those little squares, each of those symbols represents a different element. Aluminum is A and small l. Oxygen is our diatomic, and hydrogen is our diatomic. Two of our diatomics. So these elements typically exist as O2 and H2 at 1 atmosphere pressure and room temperature. Okay. Everything you can see, feel, hear, taste, whatever, everything is composed of elements in some form or fashion. Now, if it is a pure element, then it's composed of only one type of atom. For instance, iron. One type of atom, no matter how much of that stuff you have, there's only one type of atom in there. Say it's room temperature and pressure, it'll be a solid. So that's our indicator for solid. I might as well do the others too. If it's a liquid, we say this, and if it's a gas, we say that. Okay. And there's one other one that we haven't got to yet. If we put it in solution, like we put sugar, I'm not going to write the formula out, but if we put sugar in water, we'll say it's aqueous. We'll get to those later. Okay, what's a compound? A compound is any substance, matter, that is produced by a combination of elements, two or more elements combined in such a way that they cannot be separated from one another except by chemical means. They can be subdivided, broken down into smaller pieces by physical means like water or sugar. But you cannot separate those elements except by chemical means. You have to break bonds. So bonds are formed when you have a compound and you combine two or more elements. Examples, water. And by convention, this combination, this compound, is composed of one atom of oxygen and two atoms of hydrogen. So this subscript means how many of them you have. This one has one carbon and two oxygens. Notice we never write one. That's redundant. Right? If you've got the symbol there, you've got at least one of them. So we only start writing numbers when you get two or bigger. This is sugar, sucrose, table sugar. It's big. It's got 12 carbons, 22 hydrogens, and 11 oxygens. Okay, so that's how we represent compounds with the symbols. And some of these you may already know if you've started memorizing the symbols, and some of these are some of the simpler ones from the table. Now, here's another requirement for compound. A compound is only composed of two or more different elements. If you have an association of the same element, you still have an element. So for this one, that may have two oxygens with it, but it's not a compound. It's still an element. That's a diatomic element. Di meaning two atoms in the element. But if we combine two different elements together, now we have a compound. Okay, another characteristic of compounds is once you've identified the compound, then it's always composed of the same combination of atoms. Always. And it doesn't matter what the source, where it came from. If you get seawater and desalinate it and get pure water, right, it's going to be like that. If you take hydrogen and oxygen and light a match to them and they combine, they'll form water, just like that. It doesn't matter how it got there, it's still water. Right? The space shuttle used to produce massive quantities of water because the three main engines on that shuttle used hydrogen, liquid hydrogen, in one tank and liquid oxygen in another tank, and they were combined in the engines, and that's when they released all their energy and ended up as water. Okay, how many of these are compounds? Let's see. Well, we know this one is. It's got two different elements in it. Yep, two different elements, three different elements. What's Na? Memorize that one yet? Sodium. It's one of those funky ones. It's based on the Latin, natrum. This one is manganese. They're all compounds. They all have different elements in association with one another to form a unique, identifiable substance. Okay? Now, what do we mean by a pure substance? A pure substance is anything that we hold in our hand, well, if it's not toxic, we hold in our container, and we know that everywhere that substance has the same composition. There's no difference. It has the same chemical composition. I should specify that. So that's a pure substance. Distilled water is a pure substance. Iron, if we write this, we are implying that that substance that we're identifying is pure iron solid. Okay? I'd rather have this one. Pure gold solid. Or, also I've got some of this in my stash at home too. Silver. I don't have gold. I have silver because silver's cheaper. But it's pure, right? There's nothing else in there with it. So that's a pure substance of an element. But you can also have pure substances of compounds, right? If we say this, liquid, that's pure water. Okay. Or we could say we're breathing Well, primarily nitrogen and oxygen, but there's a little bit of this one in there. Carbon dioxide gas, that's a pure substance. If we isolate it, in other words, probably the easiest way to get hold of pure carbon dioxide is to go buy some dry ice. Dry ice is solid carbon dioxide. That would be a pure substance. And it, like I said, it can be either elements or compounds, but it has nothing else in there but that one substance. That's pure. Examples. Okay, now we know what a pure substance is. What's a mixture? A mixture is just a physical combination of two or more pure substances. Okay? Two or more pure substances makes a mixture. The thing about mixtures is they have a variable composition. In other words, perfect example. If we have pure water and pure salt, table salt, sodium chloride, and combine them, we can make either a very dilute solution with just a little bit of salt in there, or we can make a brine where it's almost saturated with salt. Variable composition. You can have lots of salt or a little bit of salt in that solution. That is a mixture. Okay. We normally don't think of wood as a mixture, but it is. It's primarily cellulose, but there are other things in there like those minerals I mentioned, or it also has some lignin in there, which is another natural polymer. Right? We don't need to beat that horse. But it is a mixture. Wine is a mixture, right? Water, ethanol, and various other substances. Coffee is a mixture. Right? That's why you pour hot water through coffee grinds. It picks up stuff as it comes through, and now you have a mixture. Water and a bunch of other stuff. I don't drink it, but they say it's okay. My wife didn't like it black, right? Cream, sugar. Actually, hazelnut is her preference. But it's a mixture. Now, mixtures can be separated by physical means. Right? You have the pure substances mixed together, and when you separate them by physical means, you still have those pure substances. Right? Their identities have not changed because we're separating them using physical processes. Now we have two types of mixtures. And like I said before, nature just does what it does. Right? And it's our job to figure it out, try to make sense of it. This is one of the ways we make sense of it. We define what pure elements are, what pure substances are, combine them to make mixtures. Now we know that some mixtures are uniform throughout. Right? If you take a small sample out of a homogeneous mixture and take a sample from a different location out of that same mixture and analyze them, they will have exactly the same percentage of pure substances in combination. That's a homogeneous mixture. Okay, it's the same throughout. That's what homo means same. And we give that a special name. It's called a solution. Right? All solutions are homogeneous mixtures. Example. The air you breathe is a homogeneous mixture. It is a solution of primarily nitrogen gas at about 78%, oxygen gas at about 20%. No, that's 21%. And then there's some argon at about 1%. Now, there are other minor components in there, but that's a mixture. And the interesting thing about gases is, if you take two pure substances, two pure gases, whether they're elements or compounds, doesn't matter. As long as they're gases, when you put them together, they always form a solution, homogeneous mixture, every time, without exception. And when you think about it, what does it take to make a gas? Well, you just take the individual particles and separate them way far apart. Makes a gas. They don't interact with one another significantly. So if you put two of them together, there's plenty of room for everybody, right? You got oxygen here and oxygen here. Throw a little bit of nitrogen in there, it just goes into gaps between. No problem. We have a solution, a homogeneous mixture of gases. Other substances are not quite as cooperative. Brass is a solid solution, a solid homogeneous mixture, primarily copper and nickel. Put those two metals together. Now, you can't get them together as solids, right? You got to melt them. Once you melt them and get them together, then you can let them solidify, and now you have your solid solution. And you can do stuff with it. Like you can make fittings on ships out of brass because it doesn't rust. It doesn't corrode in salt water spray. Or you can make musical instruments out of it. Okay, table salt stirred in water makes a homogeneous mixture up to a point. Right? If this were general chemistry, one things we would do is we would look at salt water that is actually saturated. In other words, it's got all the salt it can hold. And then we do stuff to it to make it either go, some of that salt comes out of solution, drops to the bottom, or whatever's down there goes back into solution. But it's a homogeneous mixture. It's a solution. Heterogeneous mixtures, now that we've hammered homogeneous, heterogeneous means hetero means other, which means that every part of a heterogeneous mixture has a different composition from the other parts. Like jelly beans. Right? If you look at a jar of jelly beans and you say, okay, there are 3 reds here and there are 2 greens there and there's 1 black one. And then you look over here, in that same space, there's maybe 4 reds, no blacks, and 3 greens. Right? So it has different composition wherever you look. Stir up some sand in water. Stir it just as hard as you can. Doesn't matter how hard you stir it. Once you stop stirring, it just goes like that. So pretty soon, the top part has almost no sand and the bottom part has a lot of sand. That's a heterogeneous mixture. Okay, and here's, well, oil and vinegar is a perfect example, right? Does anybody here make your own salad dressing? I found the best way for 1 or 2 servings is to use those little Armor chipped beef bottles with the blue caps on them. I'll make SOS out of that. And then you just clean them up. And now you put however much vinegar and oil in there together you want, and then throw some spices in there. Mrs. Dash works pretty good. And then you cap it and you just shake it like crazy. And for a second or two, it looks uniform throughout. So you get it, you pop the cap, pour it on your salad before it separates. But it will separate. Oil and vinegar do not mix. So they form a heterogeneous mixture. Sand and water already mentioned that. Which of these following is homogeneous, which is a solution? Okay, pure water. Here's a good opportunity to for test-taking technique. If you have a question that needs answering, sometimes it works best to take the question and go backwards, right? Which one of these are mixtures? Pure water? Throw that one out. Copper metal? That's pure substance. Can't be a mixture, right? So you've narrowed it down to 3. These are mixtures: gasoline, jelly beans, and soil. Take my word for it. I spent 5 years, actually 7, getting a PhD in soils. Right? I know soils are heterogeneous, right? And if anybody has lived on a farm or you do any gardening, you just dig down in the soil and you see the color, if nothing else, the color changes as you go down, but the soil texture changes too. So soil is heterogeneous. Jelly beans, we've already defined them as heterogeneous. Gasoline is homogeneous. Gasoline is a solution of octane, which is a hydrocarbon. It's a petroleum distillate. And then they add some things in there that make it more valuable and they can charge you more money for it. Like keep your carburetor clean. Or actually they mix in gasoline during the summer months. They'll mix in more volatile compounds, more volatile hydrocarbons, like heptane and hexane, maybe even some pentane. Because, no, they do that in the winter. I got it backwards, sorry. The more volatile compounds they mix in the winter, because with the colder temperatures, your gasoline needs to vaporize quickly in order to make your engine run right. But in the summer, there's enough heat, and when you first start your engine, it's already warm enough. You can have fewer volatile compounds in your gasoline. So they change the formulation with the seasons. They still charge you arm and leg anyway. Okay, that was the only solution. Okay, so if we want to separate mixtures, right, we use physical means. Right? And these are some of the possibilities for physical separation. Let's see, do I have something else up there? Yeah. Based upon the physical properties of each of the components of a mixture, they can be separated. Right? So if we know that the components have different boiling points, then we can use a process called distillation. Heat them up, and the more volatile one, the lower boiling point will come off first. Separate that one. And then when that one's gone, the next most volatile, the next highest boiling point, it'll come off. They call that fractional distillation. And that's how they separate crude oil into its components. That is huge. If you ever drive down toward Charleston and look over to the right along the river, and you'll see, let's see, I don't know what company's over there, DuPont maybe. But you'll see these big, tall stacks there. Now, they're not all stills, fractional stills, but some of them might be, because they use that arrangement for other things too. But distillation will separate your components based upon their boiling point. If they have different states, right? If you have a solid suspended in a liquid, then you can use the state, the difference between solid and liquid, and use a filter and remove them. The liquid will go straight through the filter, and the solid will be held on the filter. You can even do that with gases, but it's a little more complicated. If the substances prefer adherence to a surface, then you can pack a column with little beads of stuff. Sometimes they use aluminum oxide. And if you have differential adherence to the surface, then the things that adhere more strongly to that solid matrix will move more slowly through them. And you can pour your eluent, they call it, through the top after you put your sample on it. And you can see if it's colored, it's pretty. You can see the color separate down that column, because some adhere less and some adhere more to the substance, and you use that to differentiate between the two. And that's called chromatography. Actually, chromatography was invented for paper. to separate components of leaf extracts. Volatility. Now, this is kind of a second cousin to boiling point, but you can evaporate. If you've got two substances mixed together, one of them's volatile and one of them's not, like salt water or sugar water, you can just evaporate the water and you get your non-volatile component back. And if you have a cover over it, you catch the vapors coming off and cool them with water stream, and you can get the evaporate back also. Okay, this is what a still looks like in a laboratory setup. I can boil something here. The more volatile component comes up here, and you can tell what temperature it occurs at, and then you condense it, it drips out there. In fact, I've got a water still set up in my lab, and it separates water from the mineral components. And the only place you can get distilled water naturally is rain. And even then, it's slightly contaminated. Okay. Let's see. No chemical change takes place when you do this separation. Distillation is a physical means of separation. It gives you back your salt and your pure water. There's filtration. You just have to pick the right medium that will retain solids of a certain size. And you can separate that way. So, if you like flow charts, this is general matter, and you can have mixtures of matter. Actually, where's pure substance? There it is. Matter could be a pure substance, or it could be either a homogeneous or heterogeneous mixture. And you can separate these mixtures by physical means and give you pure substances. But if you've got a pure substance, it's either a compound or an element. And the only way to bridge the gap between compounds and elements is with chemical means. Chemical methods can be used to separate elements from compounds, just like our electrolysis of water. We used a chemical means. We drove a direct current through it, and the electrons did the work for us, separated oxygen from hydrogen. Okay, and that's it for chapter 3. So we'll, for these first 3 chapters, we didn't have anything along the lines of calculations, except for maybe scientific method, but, scientific notation. We did have calculations where you have your rules for significant figures. Right? You need to be able to do those types of calculations. And chemistry is a cumulative science. In other words, what you learn now is going to be essential for later topics. So if you do nothing else, try to master the stuff. Get comfortable with it. That's why this review document is 29 pages long and has 175 questions in it. Give you lots of practice, right? Like I said before, your best friend, curiosity and boredom. So if you don't get bored working 175 problems, then you need some more. Okay. Well, I finished early. Any questions, comments? Let's see. I'm going to go maybe another week and see who shows up for Zoom or in person, and then the rest of them are web-based, I assume.